Word up, followers. Okay, here we go. We're getting into our new section on phase changes. I think this stuff is really exciting. It's really cool stuff that we're seeing an application of all of this higher order math and physics and how it's going to manifest into something physical and tangible, like what state is something in at a given temperature and pressure. Okay, so we start by recognizing that Gibbs is our important potential with respect to phase equilibria. And that's because Gibbs is, I'm going to make this slightly thinner, Gibbs is a function of temperature and pressure. Okay, and so if I expand on this, right, we remember we came up with the equation here. Let me finish writing this and I'll describe it. So we know that the dg is the partial of g with respect to p at constant t times dp plus the partial of g with respect to now t at constant p dt. And we derived last time the fundamental equation of chemical thermodynamics. Okay, so that's fundamental equation of chemical thermo. Okay, and eventually when we go and expand on this beyond the canonical ensemble, where we're not really considering the number of moles, as we add on what happens to change the number of moles, that will give us an even better representation of the fundamental equation of chemical thermodynamics. So VdP minus SdT, and finally we realize the partial, and I'm going to switch to molar quantities, the partial molar Gibbs free energy with respect to the change in pressure at constant temperature is molar volume. Okay, so this derivative is V. And then similarly, the partial of molar Gibbs free energy with respect to temperature at constant pressure is negative molar entropy. So now what I have here to the right here is a free energy surface, okay, where we've got G on the z-axis, and then T and P represent the x and y axis. And then this would be a surface of a pure phase. So that means that could be the solid, the liquid, or the gas, okay? And we can see here when we look at the relationship between G and T, so a graph of G versus T would give us a plot where the slope is negative entropy. And if we had a plot of G versus P, the slope would be positive volume, which is pretty cool, okay? And so I'm also going to introduce a new idea here, chemical potential. And this was, I kind of briefly talked about this when I introduced the canonical, microcanonical, and grand canonical ensembles. So chemical potential is related to the grand canonical, okay? And so chemical potential gets the subscript mu, okay? And mu equals molar Gibbs free energy, okay? So it's just another name for the molar Gibbs free energy, okay? And note, it's not the change in Gibbs free energy, it's just the Gibbs free energy. So we could actually change this plot to be Gibbs or chemical potential, and that would work, all right? Okay, so moving along. So here now I'm plotting, we're just going to focus on Gibbs versus T, and also remember this could be mu versus T, this could be chemical potential versus T. And what we note, so remember here, partial of mu by partial of T at constant P equals negative molar entropy. Okay, so that's the kicker, is mu equals the molar Gibbs free energy. Okay, and it's important to note here that the entropy, the molar free energy, or molar entropy, excuse me, of a gas is greater than the molar entropy of a liquid, which is greater than the molar entropy of a solid. And all of these values, of course, are greater than 0. So that's why we see this negative slope, negative molar entropy for the slope. And what you should also note, that because the molar entropy of a gas is greater than that of a liquid, it's a steeper slope, right? And then you can see the liquid has a steeper slope than the solid. Okay? Well, let's define a few things. For a phase transition, dg, the change in free energy for a phase transition, is the following. Okay? Mu2 minus mu1, where 2 and 1 correspond to a respective phase, so 2 could be solid and 1 could be liquid, for example, okay? Times dN, the change in number of moles, okay? So if mu1 is greater than mu2, what happens? Well, if that's the case, then dg is less than 0, and we know that's spontaneous. Awesome. Okay? And of course, if it's the other way around, if mu2 are greater than mu1, then delta G would be positive, and that's not spontaneous. And of course, this is for going, I'm going to indicate that our phase transition in this way, right, it's final minus initial, okay? So this would be going from phase 1 in the initial condition to phase 2 in the final condition. So I should have set that up first. But because final minus initial, right, if mu1 is greater than mu2, then this is negative, and so that transition will happen spontaneously. Well, what if mu1 equals mu2? Okay, then dg equals 0, and this corresponds to equilibrium, or what we call on a phase diagram a critical point. Okay, so now what we have here is chemical potential versus temperature, and I want to point out here, check out what happens. There's a point on this graph where the liquid and the solid line cross. There's also a point on this graph where the liquid line and the gas line cross. And there's also a point on this graph where the gas and the solid cross. Okay? We have special names for all of these points. This point here where the liquid and solid line cross, with respect to temperature, I'm going to call that T fusion. So in other words, that's the melting temperature. Beautiful. What about this line where the gas and the liquid cross? Well, that's called T vaporization or T boiling. That's the boiling point. Super cool. What about where the gas and the solid cross? You guessed it, T sublimation. Okay? Awesome. Awesome stuff. It's a simple graph. It's a fairly simple idea, but it leads to a really powerful result here. Okay? And so what I also want to point out, what you notice here is that, let's say just a little bit colder, okay? So if we look just a little bit colder than this fusion point, look, the liquid has a larger chemical potential than the solid, okay? And so what that means is if I'm going from liquid to solid, right? Let's suppose I'm heating my material up, okay? The phase with the lowest chemical potential will be observed. So for example, Let me get a different color here. Okay. So for example, under these conditions of temperature, we're not going to worry about pressure yet, but under these conditions of temperature, this would be the observed chemical potential. Okay. The solid phase. Oh, I think I realized, you know what? Maybe you noticed this, and I was so excited about phase diagrams. I mixed up my T-vape and my T-sublimation. Maybe you're like, what the hell, Harmon? Okay, gas and liquid. Oh, wait, no, that's gas and solid. Excuse me. Look, that's the gas and solid lines. So that, rather, is the T-sublimation point. And here is the liquid and gas line. That would be the boiling point. Okay, good thing that I was zoomed way in and checking it out. So we note that less than the fusion point, the solid has the lowest chemical potential. It will be the observed phase. But now when we look at this, and as we begin to move past this, it will be spontaneous for that solid to become a liquid, okay? Because now at this point, it will meet this condition. So in other words, when we're looking at just a little bit below the fusion point, okay, the liquid has a larger chemical potential than the solid. Excuse me. Excuse me. So I'm also drawing this backwards. Jeez. Okay. Also, backwards. Hopefully I don't make too many more mistakes on this, or I might have to stop this thing and re-record. Okay, so when we're at, you know, a cold temperature, it makes sense we have a solid. So you know for your common experiences that a solid will melt into a liquid, and it will happen spontaneously once you pass the fusion point. And that is because if now I imagine my solid is my initial state and my liquid is my final state, okay? Below the fusion point, the solid has a less chemical potential than the liquid, which means the delta G would be positive. So below the fusion point, it would not be spontaneous for that to happen. However, what happens as we cross this line? Well, as we cross this line now, the solid will have a higher chemical potential than the liquid, okay? And then at that point, right, if the solid remains to be our initial state and the liquid remains to be our final state, if I were to keep going along this line, right, imagine if I kept following along the solid line, then that would actually result in a negative free energy, so the change would happen spontaneously, okay? And thus, we would now be traveling along this line, this liquid line. And you notice in this particular system, we wouldn't even have a sublimation point, at least under this given condition, right? It just passes the sublimation point altogether, because where these are now having a higher chemical potential, those phases won't exist. And then now similarly, when we get to the vaporization point, the liquid will have a higher chemical potential than the gas, which would give us a spontaneous change, and now we travel along the gas phase line, okay? So as we're increasing temperature, we're always going to follow the chemical potential lines which have a minimized free energy or a minimum chemical potential, okay? And of course, if we were to go the other way, it would be the same result, right? Like if we now have our vapor and we're cooling down our vapor, once we cross this vaporization point, now the gas has a larger chemical potential than the liquid, so it would be spontaneous for this gas to condense, okay? And this also describes why we don't observe sublimation points at all conditions, because in this case, that possibility is not even there. But in other materials at various pressures, the sublimation point actually might have a lower free energy than the vaporization point, and that's where you would observe a material to sublime or undergo deposition. okay, dry deposition. Okay, so now what about the other relationship? So again, this says Gibbs free energy, but really we recognize that we could call that chemical potential versus pressure. Okay, and so we remember mu equals molar Gibbs free energy, and also the partial of that chemical potential with respect to changes in pressure at constant temperature equals molar volume. So all of these curves represent molar volume. Okay? And we also note that the molar volume of a gas, I'm going to actually give myself much more room. We note the molar volume of a gas really is much greater than the molar volume of a liquid, which in most cases is greater than the molar volume of a solid, except water. Okay? So the solid phase of water is less dense than the liquid phase, which means the molar volume of H2O as a liquid is, the molar volume of H2O as a solid is greater than the molar volume of a liquid. So water is our exception, and there's not a whole lot of other things that have this property. You would be really hard pressed to find other materials that share this property with water. Okay? And so now if I expand on this a little bit, because you notice that the liquid and the solid are fairly constant, okay? So, for example, the molar volume under standard conditions of H2O as a gas, we know is 22.42 liters per mole. But we also know that the molar volume of a gas is subject to change. So that's why we can really see a PV equals nRT situation going on here to describe the volume of this gas. Or really, I should say, V equals nRT over P. That's really what's driving the curvature on this, okay? But the molar volume of solids and liquids, they are subject to change. They can very much change. As you know, density is a function of temperature, but they're quite stable. So the change of these things is not a whole lot. And the molar volume of a liquid under standard conditions of water is 0.0180 liters per mole. And the molar volume standard of H2O as a solid is actually 0.0196 liters per mole. So again, most of the time, the volume of a liquid should be greater than the volume of a solid, but water is our exception. Now you might be asking, how did I get these numbers? Okay, well check it out, it's liter per mole. So I got this number from using the approximate density of 1 milliliter per gram. I know that's backwards. I know you want to say 1 gram per milliliter, but I want to get this in terms of volume, not in terms of mass. So if I use, 1.00000 milliliter per gram, then that's how I get to this number, okay? And then, of course, this is from the approximate 0.9 grams per milliliter, or about 1.1 milliliter per gram. So that's where these numbers are coming from. Okay? So now, how do I get a better representation for the molar volume of a gas? Well, if I expand on these relationships here, on these partial derivatives, I can say dGm at constant T equals Vm dP. So all I did was split up these two partials. Okay? And now what I want to do is integrate from initial to final both sides of this equation. And what I get is the following. I get Gm, and I'll say at P final equals Gm at P initial. So that I did one algebra step there that I'm not showing you. So the algebra step was, this turns out to be, final minus initial. And then I added the initial over to the other side of the equation. And then now when I integrate Vm dp, and also noting, right, that Vm equals RT over P, so we dropped the N because it's now Vm that we're talking about. So when I plug in RT, right, so this is initial final of RT over P dP. And so hopefully you recognize there's going to be a natural log in there, dP over P, right? And the RT is a constant. So what I get is plus RT times the natural log of P final divided by P initial. Okay? Or I could also say chemical potential of the final pressure equals chemical potential of the initial pressure, and of course plus RT natural log of PF over PI. So that's where you see this logarithmic relationship, okay? Coming from this integral right here. All right, and so now to kind of think, okay, so what happens now when we combine both of these ideas, right? I showed you this potential energy surface. So this might be the surface of a pure phase, but how do we get a phase diagram out of this? Well, what I would need to do is calculate this surface free energy or surface chemical potential of the liquid, the solid, the gas, put them all together, right, on the same plot, and where we see them crossing like this, that's where we get phase transitions. And we note that it's not going to be a single point where they cross. Rather, it's going to be a whole series of points where they cross because these are three-dimensional surfaces. So I did this in Igor because I wanted to use data that I had. And then here's what I came up with. So this is pretty cool stuff. So in this plot here, my solid is green. Okay. My liquid is kind of this rather blue color. And my gas is this red color. And you can see that they kind of have that curvature that you saw from that previous plot. But still, how do we get a phase diagram out of this? Well, what we need is the minimums, right? So I'll play with this red curve, for example. So if I'm looking at just this slice, maybe just this slice, let's say along the 0.1 ATM, so at constant P, right? So here at 400 Kelvin, I can see my gas is the lowest chemical potential. So for water between 400 Kelvin, and then look at my scale, right? Between 400 and, you guessed it, 273, the gas is the most stable. But then now we get to this point, and what's actually really, really difficult to note here because of the way this is crossing, you might be thinking, well, what about the boiling point, 373? Well, look, that's at 1 atmosphere. I don't even have 1 atmosphere on this scale. But that boiling point, if it were on this scale, would actually be somewhere up there. Okay? Because here you can follow the 373 mark. So in other words, this curve that you see manifesting is really all of my boiling points. Okay? But now this is really difficult to see. However, you can tell there's a bit of curve crossing right there from the solid, and then there's another bit of curve crossing from the liquid. So it's really difficult to see it on this scale. So what I did here was you take this three-dimensional diagram, flip it upside down, because what you want to observe are the minima, and this is what you get. An upside down 3D graph. So we're literally, this color graph that I'm showing you. It's literally a three-dimensional graph. It's just been flipped. So imagine this plot that I'm showing you, right? We want to look at the bottom side. So it's just been flipped up to show you that bottom side. And now we're only seeing the pressure versus the temperature. And all of these boundaries here, so I highlighted them with the dotted lines because my curve crossing, this was an approximate exercise I did. where my surfaces crossed didn't turn out to be exactly correct. And I'll talk about that as we proceed through phase diagrams. There's a lot of error associated in constructing a phase diagram. So this didn't do too bad at recreating those points. So in other words now, let's go, here's temperature on this scale. All of these data points represent boiling at various pressures, okay? All of these data points along these lines represent melting at different pressures, okay? And that's pretty cool. And as you can see, you know, as my graph starts to approach 1 ATM, my boiling point is starting to approach that magic 373, 100 degrees Celsius. So this is how you make a phase diagram. Pretty cool stuff, okay? And you really have to have like an alien brain to imagine how to like flip these things around and what you're looking at and so on. So very, very cool stuff. Okay, so moving on. So I'm just going to talk about the stability of phases very briefly. And then I will probably end this lecture because I think I'm liking the shorter lectures. Maybe you're liking the shorter lectures as well. So let's just briefly talk about the stability of phases, and then I'll cut it off. So we recognize here, let me draw a phase diagram really quick, okay? So I'm just kind of drawing a fictitious one, so something like that, P versus T, and maybe this is my solid area, my liquid area, and my gas area, okay? So now what this diagram is showing you right here is if we were to start with a liquid and cool it down, so in other words, if let's say I started somewhere here and at the same pressure just decreased my temperature. Well, look, for a same given pressure, I would move that way. Let's make that a different color, okay? So I would move along this line right here. This is what I would observe, okay? This red line corresponds to this red line right here. And so what I would see is as I was decreasing the temperature, I would see that liquid cooling down. And as I crossed this point right here, okay, that point is represented by this entire area. And so if I was keeping track of the time, how long it took for my material to cool down, there would be a lag in that time as it is transitioning phases, okay? And that is due to the latent heat of the phase change, or in other words, the enthalpy of this case, the enthalpy of fusion is what's driving that constant temperature. And what's also important to note, I can never get this liquid colder than its freezing point. Now, of course, there's caveats to that. Many of you, I know, are aware of what's called supercooling. And so if we were to observe supercooling, we would actually see like a tiny region where the temperature of the liquid drops and then rebounds, okay? And so there's usually a specific set of conditions that you have to observe supercooling, okay? And I'm not going to go into that in too great a detail right now. But if we were doing this nice and steady, if we didn't have, well, actually what we would need is a nucleus. So one way you can get supercooling is if you don't have a nucleation point. So oftentimes electrolyte solutions will have supercooling because they have little particles, little ions in there that can serve as seed crystals. So I guess I did just describe supercooling, random professorial side tangents. In any event, for most pure phases, you will not observe supercooling, and you'll see this lag due to the enthalpy of fusion. Okay. So what I also want to talk about in this now, because I'm talking about time, is thermo versus kinetics. And as an example, the standard chemical potential, so that means at 298 of graphite, is actually less than the standard chemical potential of diamond. So let's think about what this means. So at room temperature and pressure, the chemical potential of a diamond is actually greater than the chemical potential of a piece of graphite. So it actually should be spontaneously undergoing a phase transition, right? So if you got a diamond, I don't have a diamond. My wife doesn't have a diamond. Say what you will. But if you had a diamond, it technically should be going under a phase transition right before your very eyes into a piece of graphite. But why doesn't this happen? Well, because the kinetics of that phase transition, the rate constant of that phase transition is crazy slow. It's got a half-life that's like the age of the universe, okay? So that phase transition happens much faster when there's more pressure and more temperature around. So even though the phase diagram might suggest that, oh, this phase shouldn't even exist right now, in certain materials, oftentimes kinetics can win. Kinetics can actually beat out the thermodynamics, okay? And so we have to be careful when we're talking about kinetics and thermo, okay? Because they often are not connected to each other, and thermo might predict one thing, but kinetics says, yeah, that's true, but it's just going to take a hell of a long time for it to happen, okay? And so let's see. With that, I'm going to end this video. That was nice and short and sweet, and then we'll pick up with the next one. Okay, folks. Hasta luego.